All right, so the first thing that we want to talk about today is the process of using analog to digital converters. So, an analog to digital converter is how we're going to basically change the continuous varying signals of real quantities we want to measure into digital numeric quantities that we can then store and analyze on our microcontrollers and computers. Right, so we need this because most of your real signals are going to be some sort of continuously varying kind of signal. Unless you're doing an experiment where you're counting number of events, you probably want to have some sort of resolution, continuously varying type number, where it's whether it's pressure, temperature, humidity, all sorts of different things. But as you've seen, hopefully, with the programming that we've been doing, is you need it to get that signal into some sort of binary format, which is in its nature a digital format, in order to be able to do anything with it in programming languages in the microcontroller on a computer. So the piece of hardware that actually does that is called an ADC, or an analog to digital converter. So basically every piece of modern electronics will have multiple ADCs in it. So for example, the oscilloscope that was used in a previous or during the oscilloscope activities, right? That was displaying a digital display, so it was taking a voltage signal and converting it to a digital signal so it could display it. And like I said, most of the types of sensors that you're going to want to use in any sort of balloon payload are going to need to go through an ADC at some point. So you're going to want to read some sort of varying voltage, usually over a period of time. So how does this work? So this is sort of a cartoon picture of it. And what you have on the top there is you just have some voltage that's varying with time. And in this case, it's just a sine wave, but it could be anything. So what happens then is basically you sample it in each of those individual little sections. So you can see on the bottom, basically either when we take that orange line, we're going to take the value at that point in time. And then we're going to convert that value into a digital number that's based on that size. So there's few key numbers that goes into that. The sampling rate is how often that we check. So in this case, how widely spaced out those orange lines on the bottom are is how often we're sampling. If we are sampling a lot, they'll be very close together, but we could be sampling, we could take a sample here, a sample here, a sample here, and a sample here. In that case, we lose a lot of the details of what's happening on those in-between times because we don't know how it's changing. So that means you have to be smart about choosing your sampling rate, right? If you're trying to look at something that is changing very slowly, a slow sampling rate is okay. But if you're looking for something that's changing rapidly, well, you need to have a much higher sampling rate. And the way you're going to determine this is, one, you're going to look at whatever your science requirements are. You're going to also be constrained on your processor speed, right? There's some upper limit to how fast you can actually read in values. And you're also going to be sort of constrained by your storage capacity because you're not beaming these numbers down, you have to store them on some sort of permanent storage media. In this case, you will most likely be using an SD card, which is actually a very large storage area, capacity storage device. But previously, what was used was like an EEPROM, where you would maybe be only able to store like 1,000 values total. So as we increase the sampling rate, we get more partitions and we get more data points. And that can help us increase the accuracy of what we're trying to measure. And if we remove it, the opposite happens, obviously. But as you add more samples, you have to store those somewhere, and you have to spend more time processing. So it's a trade-off is where you basically want to determine how quickly do you need to sample. Because one, if you have a lot of extra data, that's hard to deal with, and also you might run out of storage, or you might miss some other part, some other measurement that you're trying to get because you're spending too much processing time checking something that's not very important. So basically, the idea of how you choose that is you want to go in with having an idea of how quickly the thing you're measuring is changing. So from that, you can get, so for example, if I'm talking about the height, the altitude, I have an expected ascent rate that of the flight. In this case, I expect to be rising, the balloon rising 1,000 feet per minute. So then I can look at things like temperature and pressure curves that compare the altitude to temperature and pressure. And from that, I can get a rate of change on temperature, pressure, other variables. Then I can also look at, well, how sensitive do I want to be? Do I want to be able to tell 0.1 degree changes or just 5 degree changes, right? If I'm looking for a smaller change, that means I'm going to need to sample faster. So once you get a number of, okay, if I'm trying, I want to take, because I want to see a 1 degree change and I expect it to change by 5 degrees over a minute. Okay, now I can assume then I only need to sample 5 times a minute. And then you double that basically to make sure that you're sensitive to any changes. In particular, if you have something that's oscillating between like a positive and negative value, right? Like our sine wave back here, I want to make sure I can see that it's going positive and negative. Because if my sampling rate is only at these 0 crossing points, I won't be able to tell the difference between something like this where it's actually oscillating positive and negative, or something that is just straight negative or straight 0 the entire time. So that's why you double it. And this has a particular name. It's called Shannon's sampling theorem, but that's not important. What's important is the methodology of how you choose that. So, like I just said, you look at your requirements. So what sort of accuracy of measurement, what are you trying to observe? And then you look at how fast can you sample it and how much storage space you have. And from that, from all of those constraints, you're going to pick how often you sample. So here's an example that I sort of talked about in broad strokes, but here's with specific actual numbers. You want to observe temperature changes from ground level up through 100,000 feet over the flight. You have a microcontroller that has a 16 megahertz clock. It can see, it has a 10-bit resolution on the ADC. We'll talk about what that means a little bit later. And then our storage is a 5 gigabyte SD card. So if we look at a particular model for how we expect the temperature to change with height, we see it changes 3 degrees every 1,000 feet. And we expect, like I said, to rise with 1,000 feet per minute, and we expect a total flight of 4 hours. The sampling rate of the Mega is 125 kilohertz. So this is how often we can take a sample. So that means doing the math, you can take, roughly 60,000 data points a second. And the SD card can store a lot of data. This has become much less of a concern as non-volatile storage has become better and better. So these days it's fairly easy to get an SD card, something small with no moving parts that keeps its storage when it loses power, on the order of 100 gigs, 200 gigs, 30 gigs. So in most cases these days, you're not limited so much by the storage size. Right? So continuing on, we want to see temperature changes of 1 degree. So based on this 3 degree per 1,000 feet and 1,000 feet per minute, that means 3 degrees per minute. So that means 3 data points per minute per every 4 hours. But again, we would want to double it. And based on that, you can get a collection rate of roughly 0.1 hertz, or 1 sample every 10 seconds. And down here just goes through the math. And if you calculate the storage, how much this will take, you can say, okay, I'm going to do this for 4 hours. This is just a conversion from hours to seconds. That's going to tell me how many data points I need. So 14,400 data points is how many I expect to take. Each one of those is 10 bits. So I need this total amount of storage. But this is less than 1,000th of the capacity of the SD card. So we're not particularly worried there. One key thing here is actually, so this uses it says 10-bit. So that's based on the resolution of the ADC. But actually, when you're storing the numbers on the SD card, it probably won't let you store just 10 bits. It'll probably require you to take a full 16 bits or 2 bytes. And that just has to do with how the blocks are set up on the SD card. But like I said, even if we're off by a factor of 2, we still have plenty of storage. So what is that resolution that we talked about? So the resolution is set by the actual piece of ADC hardware. In this case, it's the microprocessor, the Mega's ADC, but it is also possible to get external ADCs that have different resolution. And in this case, the Mega has a 10-bit ADC. So that means every time you read in an ADC value, you'll get a 10-bit number. So that means if you look 2 to the 10, that means there's 1,024 possible values. So I can get every integer number from 0 to 1,023. And basically, each one of those numbers is going to correspond to a voltage between 0 and 5 volts. So you take the entire 0 to 5 volt span and you divide it up into 1,024 different pieces. And each one of those individual voltages that you've divided up will give you a single binary number. So, and same sort of thing as sampling rate. You can get a higher resolution ADC. You can get, 16, 14, 20, there's components out there that you could find if you really wanted that, but it's going to require more memory. And also at some point, if you have a very high resolution ADC, well, if your signal noise is bigger than each one of your little ADC pieces, you're not really gaining anything. So how do you convert? Well, like I said, you basically take the full span, you divide it over by the number of individual measurements. So our resolution of the ADC is 1024 or 1023 in this case, because 0 is what we're assuming. The total voltage is 5, and if we were to put in, it's just a simple consistent ratio sort of thing. So if we were to put in 2.12 volts, we could then solve for the remaining thing and give our ADC value. And in this case, it would be 434. And you can go the opposite way as well. It's just a simple linear relationship. But that is something you actually want to check. So most ADCs are linear, but you could have potentially a different range or a different sort of relationship depending on the application. And if you look up the specifications for the ADC, it'll tell you basically how linear it is. So one thing, there's a few tricks that we can do sort of to make the most of our resolution. So a lot of times it's easier to change the signal going into the ADC than change the resolution of the ADC. So we do something called signal conditioning. So we basically take the input signal, run it through some circuits, often amplifiers, to change the signal. And what we're doing is we're trying to change one analog signal to another one. For example, if we have a signal that is only varying from 0 to 1 volt, but our ADC is a full 0 to 5 volt, well, we want to take advantage of that whole 5 volt resolution. So we would take our 0 to 1 volt signal, run it through an amplifier that would amplify it by 5. That way we can get the full advantage of that resolution. An even more obvious example is if I have a signal that has a larger range than my ADC, right? If I have a 0 to 12 volt measurement that I am trying to do, but I only have a 5 volt ADC, Well, I don't want to just feed that directly in. In worst case, you could damage the ADC, but what will most likely happen is basically you'll get the max ADC value anytime you were over 5 volts. So anything from like 5.01 to 12 volts would give you the same number, so you wouldn't be able to tell. So like I said, we either do amplification, which is when we're making a signal larger, or attenuation, which is when we're making it smaller. Or we can adjust basically the base and span. So where the zero is of our signal and how wide it goes to. So, for example, the temperature sensor that you guys are going to use later on in the Megasats is based on a diode, and the signal is actually going to change on the order of 450 millivolts to 800 millivolts. So that's from 0.45 to 0.8 volts, right? So that's actually a very small part of our ADC signal, and if we didn't do any sort of signal conditioning, we would not be sensitive to a lot of those changes. So you would run it through an amplifier, and basically you're going to construct a circuit that's going to give you a linear relationship. So where basically 450 is going to go to 0, 800 is going to go to 5 volts, and it's going to just be a straight line between those 2 points. And in this case, like I said, we use these terms called the base and the span. So the base is the lowest expected measurement, and the span is the width of the total measurement. So in this case, our original signal, the base is 450 millivolts, and the span is 350, right? It's just the highest value minus the lowest value. And what we want to do is change it to a 0 to 5 volt signal. So another thing that you often want to do is basically clean up the signal. You're trying to remove some noise that you're not really interested in. So you can see this is, again, just sort of a cartoon picture. And the idea is that we're interested in these big, slower changes, and this little small, much more rapid oscillation is some sort of noise, electronic noise. So we could run that through a filter and basically sort of average out over these small oscillations, and we would get a smoother signal. So you may recall that we talked about the Arduino having ADC pins, specific pins, and those pins are labeled A0 through A15. So there are 16 of them. And the way that you read that value, you initiate that ADC conversion, is through this command in the programming software, the IDE. Analog with an uppercase R read. And then you put either the pin number, or you can use the constants. I don't know if you remember that, but if I put capital A0 in where this pin is, it'll read A0 because the Arduino has a defined set of constants. So A0 will map to whatever the number is. I don't remember off the top of my head. And as we've talked about a few times now, it is a 10-bit ADC. So when you call this function here, what it will return is a value from 0 to 1023. So again, you'll want to save that to a variable, most likely, because if you're reading this voltage value, that means you probably want to do something with it. So you would, basically do variable equals analog read A0, right? And now you have that value stored in a variable, and you can do whatever you like with it. You could write it to your storage. You could do some calculations. It sort of depends on what your goal is. And that is it for the analog to digital conversion lecture.